Hey everyone. I was having trouble with my camera and my microphone this morning, so I had to fix it.
Hello.
Hey, you?
Hi. Are there going to be office hours today?
Absolutely. Office hours today and tomorrow. Usual
Okay.
time 12:30 to 1:15.
Okay, thank you, because I'm confused on some of the homework things.
It's a good time to ask.
Yep.
All right, let's give it just a minute. I think more people are joining, and then we'll get started. Do this. All right, just as a reminder, you guys, we have a quiz tomorrow. So quiz tomorrow, it'll operate like our usual quizzes where it'll open up Thursday afternoon at 4, and it'll be available for a 24-hour period, just like everything else. Hang on. Just like all the other things that we've had, quizzes and tests and whatever. I don't know why things are beeping so much. Hopefully we can get that to stop. And homeworks are also going to be due tomorrow night at midnight. So like I said before, we have office hours today from 12:30 to 1:15, and again tomorrow from 12:30 to 1:15. So if you have any questions about the stuff and you want to come by, we can work it through. Okay. Okay, great. So let's go ahead and keep talking. So we were talking yesterday about chapter 3.7, which looks at when we have multiple, like two, we're talking about two random variables that are happening within, say, some kind of a context, like an experimental context. And so we want to be able to describe their joint distributions. Okay, so we talked about yesterday before we had we talked about their probability. Things they keep beeping so much. Their probability mass, their joint probability mass functions for discrete random variables, and then their probability density functions for continuous random variables. So now we're also going to be talking about, let's see, we want to talk about cumulative distribution functions and how we can do that when we have a joint distribution that's happening. So I'm going to pick up chapter 3.7 and we'll finish off that chapter. Go through a couple more examples, and then we'll move on to chapter 3.9. Okay. All right. So chapter 3.7. So today we're going to talk about a joint cumulative distribution function. Okay. So remember our cumulative distribution functions. These things. Hang on. Get this right. So a cumulative distribution function, remember, is one that takes our probabilities, okay, and it accumulates them, right, as we progress through our possible values. Okay, so we start off at whatever our minimum, our base level is. Often it's 0 before things get defined, and then it's some value. And then as we progress through, once we max out what our range of values is for our probability mass or density functions, then it continues on at 1 for the rest of it. Okay, so once we've accumulated all of our probabilities, we stay at 1, right? 1 being our maximum probability that we can have. Okay, so first, before I jump into all of these, let's talk about some properties for joint cumulative distribution functions. Okay, so we're going to say, let's make sure that you can see that. So f sub x of x is going to equal to our joint distribution function x to infinity. Okay, so this is like saying I'm going to go from my values of x to infinity. This is, we're dealing with our cumulative distribution function for x. My second, we're going to actually work through examples using this and talking about it. So I'm going to list the properties here. It's going to seem kind of esoteric. It's going to take some time to kind of think it through. But when we work through the examples, then these things will become more clear exactly how this is getting used. So in terms of y, f x y, this is going to be infinity to y. Okay, all possible values of y and whatever our values of x, all possible values of x and y. 3. fxy. Right, so once we've progressed on, towards infinity, our joint distribution function cumulatively has accumulated all of its probabilities. Okay. So this is an important property here. This one says x, y of minus infinity to y is equal to f xy x minus infinity equals to 0. What this means is, right, when x is negative or y is negative, right, these values are going to be 0 because all of our our accumulated probabilities need to be positive. Must be 0 when in a negative area, like a quadrant. Like when x is going to be negative or y is going to be negative. Okay, so 5, our fifth property that we want to think about, probability that x1 is less than x is less than x2, y1 is less than y is less than y2, and that's going to equal to f xy x2 y2 minus f xy x1 y2 minus f xy x2 y1 plus f xy x1 y2. So this is like saying before when we had like the probability, when we just had a single random variable, the probability, right, that x was between two values, okay, a and b, say for example, I can use my cumulative distribution function to help me figure out what's that probability. Because our cumulative distribution function is accumulating all the probabilities along the way. Okay, so now with the joint distribution, okay, if my x is between two values and my y is between two values, okay, what I'm taking a look at is my joint distribution for x2, y2 minus the different combinations, but then I have to add back in the things that I would have subtracted out. Okay. 6, if x and y are independent is important, independent, then we can say fx y is equal to f of x times f of y. Okay, this is important, right? If things are independent, also a way that we can prove independence too. Okay, and then right, let's see. X, y equals probability that x is less than or equal to x and y is less than or equal to y. So in this case here, right, we're still accumulating probabilities.
For number 5, should it be plus fxy of x1 and y1 instead of x1 and y2?
Yes, sorry, yes, thank you, that's a typo. Thank you.
Yep.
Okay, so x2, y2, x1, y2, x2, y1, and then x1, y1. Thank you. Okay. This we're still accumulating when we're within some range of values for which our random variables are still being defined. It seems a little esoteric, you know, when I just list these properties. We're going to see it put into action when we work through some examples. Okay, so if you guys a minute to finish writing that down, and then take out your example sheet for 3.7, and then we're going to take a look at example 7, which is where we left off last time. Okay, so let's take a look. So example 7 says we've got these two random variables, x and y, and they're independent. So we're told from the start that they're independent random variables, and they're in a uniform distribution. And so we want to be able to find the cumulative. Yeah, you bet.
Sorry. Okay, thank you.
No problem. All right. So example 7 says we've got these two independent random variables. We're told from the start that they're independent. And they're in a uniform distribution from 0 to 1. We want to be able to find their cumulative joint distribution, big F, x, y. Okay. So uniform distribution, let's just talk about what this looks like. So uniform distribution, right? It's where all the probabilities are equivalent. This 0 to 1 basically tells us that we're going like this right? And then, this can continue on from here, but the distribution that we're looking for is from 0 to 1. So we're looking there, okay, from 0 to 1. That's what we're told here. Okay. So now we want to be able to do is find their joint distribution. Okay, so I think what I'm going to do is from our uniform distribution, I'm going to come up with my individual cumulative distributions for f and for x and for y. So for f, x, okay, I've got 0 when x is less than 0. I've got x when x is between 0 and 1. So I'm saying it's x, whatever my value for x is between 0 and 1, okay, whatever I happen to have for that x value, and it's going to be 1 for x is greater than 1. Okay. By being told that it's a uniform distribution, I can, and from 0 to 1, I can actually cut things out and I can come up with a lot of information because this uniform distribution gives me information about it. Okay, so that's our marginal, right? This is for our x variable. Let's do it for our y. It's the same thing. So 0 when y is less than 0, it's going to be y when y is between 0 and 1, and 1 when y is greater than 1. Okay, so this gives us our individual x and y values. Okay, this is a cumulative distribution for those. Okay, so since they're independent, we can do things because they're independent. We're told that they were independent. Now, one of the properties that we were given at the start of this said that if they're independent, then the joint cumulative distribution is the product of the individuals. Okay, which means I can then plug in what I have and then specify what my ranges are. Okay, so that means, let's see, I'm going to plot it out just a little bit just so we can see, because we have all these different ranges. We have to think about when x is 0, when y is 0, I mean, when x is less than 0, we have to think about all these different spots. So let me come up with a little mini graph here so we can visualize what we're doing. So here's 1, here's 1. Okay, now this is the region that we had shaded out before. This is where our distribution is going to have a value f, right, between 0 and 1. Here's x, here's y. So now we want to think about what's happening within these regions here. Okay, so now when x is negative, right, when x has a negative value, my cumulative distribution is going to be 0. When y is negative, my cumulative distribution is going to be 0. So this is f x, y. Okay, and this is a 1 right there. Okay, so all these values, right, when x is less than 0, when y is less than 0. Okay, so now I'm going to start kind of building things up a little bit off to the side, x, y, and it's going to be equal to. Okay, so this is going to be equal to 0 when x is less than 0 or y is less than 0. Okay, that's here or here. That would be 0. All right, now the next part is, right, we said that because they're independent, right, I can then multiply together their individual cumulative distributions, right? So that means this is going to be x, this is going to be y, and that will be valid when y is between 0 and 1 and x is between 0 and 1. So I'm going to write that down. So xy is my next function on my cumulative distribution. So I'm going to write 0 less than or equal to x, which is less than or equal to 1, 0 less than or equal to y, less than or equal to 1. Okay, then that's where this is valid here. Okay, now we have to think about these other options. Okay, so let's kind of write in here, I'm going to put it in a different color. Here, xy, in this portion. Okay, now when I'm up in this portion here, right, I'm going to kind of do this, build it out just a little bit. Okay, so when x is between 0 and 1, but y is greater than 1, it's an option, right? And what's going to happen is x, y, this whole thing's going to be equal to x. You can think about it as x times y, but y is equal to 1, so this whole thing is just equal to x. Okay, So now I'm going to write that down like this. This will be x when x is between 0 and 1, and when y is greater than 1. Okay. Now, likewise, okay, over here, right? Actually, let's do it over here. So when here in this spot, this is a spot where x is greater than 1, but y is less than 1, okay? Which means that x has already accumulated all of its probabilities, so x is equal to 1. Then our joint cumulative distribution is equal to x times y, but x is equal to 1. So it's just plain old y. So this is going to be x is greater than 1 and y is between 0 and 1. Okay, and our last bit is right here, okay, where both x and y are greater than 1. And we've essentially accumulated all of our probabilities by that point. Okay, so this is going to be 1, so this is going to be x is greater than 1 and y is greater than 1. Okay. But knowing that it was a uniform distribution, right, helped me figure out like what the individual probability cumulative distribution functions were. And then knowing that they were independent variables allowed me to come up with their joint cumulative distribution. Okay. If I didn't know that they were independent, I would have to have other information to help me build those. Okay. But knowing that they're independent, I can exploit that property. Okay. So this you don't have to do, but right now while we're learning it, this is going to help you visualize what it is that we're trying to do. The different aspects, different areas of our cumulative distribution function that we need to take into account. Okay. I'll give you guys a second to finish writing that, and then we'll go on to our next example. Okay. All right. So I'm going to flip the page to example 8. All right. So example 8 says, we've got x and y, two jointly continuous random variables with a joint PDF, and we're given our joint PDF, right, lowercase f. So we're talking about a probability density function, not a cumulative. X plus c, y squared. You see a c, that means that we're going to have to figure out what's the value of c that's going to make this a valid probability density function, and 0 otherwise. So it's going to be when x is between 0 and 1 and y is between 0 and 1. Okay, so now, right, we have to find c first off so that we can get our joint probability density function. And then we're going to start answering questions about probabilities. And then we're going to take a look at our marginal PDF value. So we want to pull out our individual function for the probability density function for x and then one for y. And we want to find the joint cumulative distribution function. Okay, so what I'm going to do is, since we're still learning how these things look, I'm going to kind of do a rough sketch. You don't have to do these sketches, but just so you can start to visualize what this looks like. So this is kind of like, so this goes out to 1, this goes out to 1, okay? And then I've got this x plus y, some kind of constant times y squared. So I've kind of got this a little bit like that, but this thing, you know, kind of pulls up, right? Because of the y squared function, and then it goes up to some value. And let's see if I can draw this out. This, and then this part's going to go up like that. And then this part kind of pulls up a little bit, and then it kind of goes up like this. So we're talking about like a 3-dimensional structure here. Okay, it's kind of how we're thinking about it. I hope you guys had a chance to take a look at the 3D surface plotter. I posted a web link for it yesterday afternoon. It's really going to help you, once we figure out like what C is, you can plug it into the 3D surface plotter and then take a look. This is just one view on that. I really like it. You can actually take your mouse and, you know, move it around so that you can kind of see all the different angles for how this looks. Okay, so just a rough sketch for, you know, how we can visualize, because when we're in 3 dimensions, so we're talking about a volume here. All right, so first part, we want to find C. Okay, so that means that I have to think about, let's remember, I have to integrate my joint distribution, right, dx, dy, I have to integrate that over both x and y, and the volume, the total volume of that has to equal to 1. Remember, all of our probabilities have to sum to 1. So that means that we have to figure out what value of c is going to make that possible. Okay, so I'm going to plug in my function that I was given, and I'm going to plug in the bounds that we were working with. So 0 to 1, 0 to 1, that was defined here in our function at the beginning. X plus c y squared dx dy. There's a reason why I could go dx dy, I could do dy dx, it doesn't really matter. Although I've got this constant in front of the y, so maybe I want to process the x part first so that I can deal with that, but it's probably going to come out easier, same either way. All right, so now I'm doing x first, so the y functions pass through as though they were a constant. So I'm going to get 0 to 1. This goes with the power rule, x squared over 2 plus c x y squared. And this is all evaluated from 0 to 1. And then we have to integrate now our y value. Okay, so once I plug this in, remember this is a power rule, right? So this is a constant term times dx. So I have an x here that I now loop on. Okay, so now once I evaluate that, I'm going to get 0 to 1. I'm going to get 1/2 plus c y squared dy. Okay, once I plug in, okay, remember I'm evaluating my x values. Okay, the y values we're going to do right now. So I'm going to integrate this, right? 1/2 plus cy squared dy. This is in terms of y. So I'm going to get 1/2 y plus 1/3 y squared times c. And this has to go from 0 to 1. Okay, when I go ahead and evaluate this, right, I'm going to get 1/3 c plus 1/2 equals 1, right? And then I'm going to subtract the 1/2. I'm going to get 1/3 c equals 1/2, and then c is basically going to equal to 3/2. Okay, this equaling to 1, right? I said this equal to 1 right here comes from our initial property of, right, all the probabilities need to sum to 1. Okay, so I didn't just pull this one out of thin air. Okay, so all the probabilities need to sum to 1, so that's how I can find out what my c value is that will enable all of these probabilities, this volume under our shape, to sum to 1. All right, so c is equal to 3/2. So now we have our fully functional joint probability density function. Okay, we know what our c value is. Okay, so we can start answering other questions. Okay, so part B says we want to find the probability that x is between 0 and 1/2, and that y is between 0 and 1/2. Okay. All right, so let's go ahead and think about that. So the probability that's going to equal to, we're going to say that this is, I'm going to go from 0 to 1/2, 0 to 1/2. These are my bounds right here that were given to me in the function. I'm going to go x plus 3/2 y squared. This is my probability, joint probability distribution function. Dx dy, it doesn't matter in this case. I think if I do dx dy or dy dx, they're both equally the same. Now I'm going to start integrating, so I'm going to get 0 to 1/2, 1/2 x squared plus 3/2 y squared times x, and then this is from 0 to 1/2, and don't forget we now need to evaluate by dy. Okay, but I'm going to first plug into my fundamental theorem of calculus, okay, because I have to evaluate the x's between 0 and 1/2 before I integrate again. I'm going to get 0 to 1/2, and that's going to look like 1/8 plus 3/4 y squared dy. Okay, and when I integrate this out and I apply the fundamental theorem of calculus, I'm going to get 3 out of 32 is my probability that x is between 0 and 1/2 and y is between 0 and 1/2 on our joint distribution. Okay. Parts A and B. I'll give you a second to finish writing it out, and then we'll move on to C and D. Okay. So part C. Part C says we want to find our marginal probability density functions. Okay, so let's think about how we're going to do that. So I have to think about my x values. So my x's are going to go between 0 and 1, and I need to integrate integrate over all x values with respect to y. Okay, remember we did this with the discrete functions? Okay, it's a little easier to kind of conceptualize what we're doing. We're doing the same thing, but we're integrating, we're summing up our continuous function. So my probability density function for x is going to look like I'm going to integrate over all x, right? X goes from 0 to 1. My joint probability distribution density function, y squared dy, and that's going to look like xy plus 1/2 y cubed from 0 to 1. Okay, and this is, I'm going to plug in values for y because I did dy, so I'm evaluating my y values. And so that's going to look like, I'm going to put this together, so it's going to be x plus 1/2 when x is between 0 and 1, and it's going to be 0 otherwise.
So you evaluate from dy when you're trying to solve for x, and likewise you do the opposite for the other?
Exactly. So remember, it's a little easier to conceptualize when we did the discrete functions, right? We had the table, and then we had our random variable for x. We had the, for y, and then we had the random variable for x, right? On the one was a set of columns, one was a set of rows. And if you'll remember, if x was equal to 0, we summed across all of the y values, and we got a probability. So we said when x is equal to 0, the probability is this. When x is equal to 1, we summed across all of the y values, right? We got another probability. And now when we did the y, right, we said when y is equal to 0, for example, we summed across all of the x values and got a probability. These summations for each column built up our probability mass function, right? There are individual probability mass functions for y and then for x. We're doing the same thing now, but with a continuous variable, we sum up by integrating, right? So across all of our x values, our x is defined between 0 and 1, right? We're going to integrate, we're going to sum up across all of our x values, right, with respect to y. So it says, you know, I'm going to look at this particular x value, what are my y's? For this particular x value, what are my y's? That's what this means, okay? So we're saying I'm going to sum up across all of my different x values, right? I'm going to take a look at the different y's that we have, okay, with respect to the y. It's the same process, but the summation in continuous form is an integral. Okay, so let's do the same thing now for y. Right, so we're going to integrate over all y values with respect to x. Okay, we're going to do the same thing that we did for the x, but now we're going to do it for y. So I'm going to say my fy of y is going to look like, right, from 0 to 1, x plus 3/2 y squared dx, right? So now we're doing dx, whereas before we did dy, right? So I'm going to do this. This is going to look like 1/2 x squared, my power rule, plus 3/2 y squared times x, right? And that's going to be evaluated from 0 to 1. Okay, so I'll just start putting that right into my function. Okay, so the way this is going to look is 3/2 y squared plus 1/2 when y is between 0 and 1. And it's going to be 0 otherwise. And these are what we call marginal probability density functions for x and for y. So we took our cumulative, right, which was our joint, we took our joint probability density function, right, and then we kind of pulled it apart by summing across x in order to get y, summing across y in order to get x. Okay.
For the bounds of the integrals, do you use the like range for the y for finding the marginal PDF
Yeah.
of the y?
And like, why didn't I go from 0 to x or y to 1 and all that kind of stuff? And it's partly because it's how it's defined when we did our function originally. So our original function was defined like this. X, you can kind of almost think about it as like they're being independent, right? And I don't know yet if they're independent, but let's just, I've got this x and y have this, they're defined separately. So x goes from 0 to 1, y goes from 0 to 1. Whereas on previous examples, let me bring out, on a previous example, this was example 6, right? So we've got y goes from 0 to x, right? And then x goes from 0 to 1, Okay, so how, or you can even think about it as it's going to go from y to 1, okay, and then y goes from 0 to x. So because it was defined as with a sort of an inherent dependency on it, right, then how I came up with my individual marginal distribution functions, right, I needed to take into account that x and y had these kind of built-in dependencies, right, whereas here, I don't know for sure, you know, if they're independent or not, but I need to be able to work with the bounds that were given to me here. X is between 0 and 1, y is between 0 and 1. Specifically, I was told at the beginning. So I'm using these to help me figure out how I'm going to come up with my marginal EDFs, which is how we got these bounds here. Okay, so I worked with what was given to me in the beginning. Okay, there's no like, sorry?
In the last problem, for
This one, right?
example 7,
Huh?
How did we get the graph of y is equal to 1 and x is like that one up top?
Right here. That's what it, so I'm trying to pull out examples using a uniform distribution because we don't actually specifically define it for you, but uniform distribution is a very common distribution type. And so I want to, you know, try to pull out examples that use it as often as I can so that you get familiar with seeing what it looks like. A uniform distribution, like we have done it in the past when we've had like in discrete cases when we had the fair die. So it's a 6-sided die, right? So if I roll, if it's a fair die, then the probability of me getting a 1 or a 2 or a 3 or whatever is the same. It's 1 out of 6, which makes it a uniform distribution, right? That's a discrete case because it's just a die. But here, a uniform distribution is completely flat, right? It's doesn't change. It doesn't like have a, you know, like sort of a bell-shaped curve. You know, things aren't concentrated around some central tendency. It's the same no matter what x value we have. Our uniform, our distribution is, our probabilities are the same. Okay, so this here, like I said, I'm trying to use the uniform distribution a lot because we don't actually, you know, give you like these are all the different types of distributions that you can have. I try to do some kind of summary towards the end once we've talked about all the different distribution types, just so you can see what they look like generically speaking. But in order to use them, right, you have to know what does it mean to be uniform distribution between 0 and 1. So we're graphing it out just so you as a class can see what a uniform distribution looks like. Okay, so that's how.
So if it said like a uniform distribution from like 0 to 2, how would that?
Yeah, so if it was from 0 to 2, then we would have to adjust. We'd probably have to have some kind of coefficients on here in order to make sure that the probabilities are going to sum to 1, essentially. So we would need some kind of coefficient on there. But typically, our uniform distribution is going to go. We usually typically say it goes from 0 to 1, 0 to 1. But like I said, if it goes from other numbers, right, then I need to have some kind of coefficients here to make sure that my probabilities sum to 1.
Okay, thank you.
But we'll keep bringing these things up. Like I think I'm trying to remember when I do it. At some point in the semester, I'll do some kind of a really rapid, quick summary of the different distribution types. So chapter 4.2 is another common distribution type called the Poisson distribution. It's a specific shape. And it happens in certain instances. We'll talk about it tomorrow. The normal distribution, which is our common bell-shaped curve, is a super common. That's the one that kind of happens most naturally in the world in experiments, and especially when you're dealing with binomial experiment types. So if I ask, does this work, yes or no, typically things tend to move into a normal distribution, a bell-shaped curve on their own. But you could get Poisson distribution as an underlying probability distribution, or you could have a uniform distribution as an underlying probability distribution. So at some point, I'll summarize what these things look like so that you can just get a visual, you know, and then you kind of know like what the standard form for the equations are like. So I'm trying to pull out examples using these things because we're not really defining it per se, right? So you can get familiar with it because it does pop up a lot. All right. So example 7, example 8. Okay, so let's keep finishing. So we're on example 8 still. So we did C. Now we want to talk about part D, which is we want to find the cumulative, the joint cumulative distribution function. Okay, so we want to find our joint cumulative function, right? All right, so now let's think about, I've got my, I'm just going to write down my probability density function that's joint. So I've got x plus 3/2 y squared, and this is 0 is less than x, which is less than 1, 0 is less than y, which is less than 1, and then 0 otherwise, right? Because our cumulative is based on our probability density function, right? So let's think about what we're going to take the low-hanging fruit, right? Where is our cumulative equal to 0? Where is it equal to 1? And then we'll launch into the calculus to find out the specifics on what are our specific values. All right, so now we know our cumulative distribution function is going to equal to 0, right? When x is less than 0 and y is less than 0. Okay. We also know that this cumulative distribution function is going to equal to 1 when x is greater than or equal to 1 and y is greater than or equal to 1, right? So this is kind of like our low-hanging fruit. We're going to put it all together at the end, but just knock off the easy parts first, which is where is it 0, where is it 1, okay? All right, so within the bounds between 0 and 1 for each of these things, we need to be able to find out what is our joint cumulative function. All right, so what I'm going to do is I'm going to kind of switch some variables here just to help me kind of think about how I'm going to integrate. So I'm going to think x, y, and that's, I'm going to go minus infinity to infinity. This is my generic formula. So I'm now going to start thinking about my other ranges of values for my x and y. I'm going to think f, x, y, x and y. And I'm going to think about, you know, integrating with respect to du and dv. This is just like so that I can kind of handle the different variables that's in x. Okay, so now I need to go from 0 to y, and I want to go from 0 to x, okay? And I'm going to think about, instead of x, I'm going to think about that in terms of a u, and then instead of y, I'm going to think about this in terms of v. This is just an alternate way of thinking about it to help us kind of work it through, just so you can see different tactics for coming up with this function. Okay, so now, let's see. For 0 is less than x and y is less than or equal to 1. Okay, so I'm going to think about this as my first bounds here. So I'm going to say my cumulative xy equals 0 to y. Like I said, I'm sorry, I already wrote this one. So this is going to look like, okay, so I'm going to start integrating this one. So I did 1/2 u squared plus 3/2 v squared u, and I'm going to go from 0 to x. Okay, and then I'm going to put this, and you don't really have to do this. Before, when we were doing it, we just kept it as x and y, and then we still evaluated. We just had to keep track of what it was that we were actually doing. But let's see, and then dv. But now we're just switching variables so that we can now plug in and get things in terms of x and y. So this is going to look like 0 to y, 1/2 x squared plus, whoops, that's a 3/2 x v squared. And now we're going to integrate this with respect to v. Okay, it's just a substitution of variables. Okay. So now this is going to be 1/2 x squared y plus 3/2 x y cubed. Oops, sorry, I actually substituted these things back here. So I integrated, right, with my power rule. Did I get what?
How'd you get the bounds for 0 is less than or equal to x and y is less than or equal?
Yeah, so this is like basically we're looking at our values. We're saying that we're essentially doing, this is like saying our x is between 0 and 1 and our y is between 0 and 1. Okay, I'm just kind of writing it in a slightly different way just so you can kind of see how we can do it there. But x is going from 0 to 1, y is going from 0 to 1. We are coming up with a function, so I'm going to go, I'm looking at summing across, right? If you think about what we did when we're creating our cumulative distribution function, right? I'm summing up as I go. So what's my y value as I go, and what's my x value as I go? So I'm going from 0 to y, 0 to x, okay, as my bounds, right, as I'm putting it through. This is, we've already done where x is less than 0, y is less than 0, x is greater than 1, y is greater than 1. So now we're looking kind of more at the meat when things are happening. Okay. Okay. There's a lot to take in here. There's a lot of details. Okay. So kind of write it down, and then you'll get a chance to practice these things on homework, and we can answer questions, but some of this stuff is you know, kind of like detail pieces. Okay. But write it down, think about it, and then we can talk about like details about how did this work and why did we choose these things. Okay. So now let me summarize this. So f(xy) is equal to 1/2 x squared y plus 1/2 x y cubed. Okay, oops, and then this was between 0 and y. I needed to evaluate that. Okay, so now I'm going to think about a range where y is greater than 1. X is still within our bounds, but y is going to be greater than or equal to 1. Okay, so that means that my cumulative, right, is going to equal to f of x, y, x, and 1. Okay, because y is greater than or equal to 1. We've already accumulated things, so y is functionally equal to 1. So that's 1/2 x squared plus 1/2 x, right? So wherever I see my y values, I plug in a 1 because y has already accumulated all of its probabilities at that point. Okay, so this is another piece. And we're going to put all these things together into a big piece. All right, so let's do the last combination here. So for when y is still between 0 and 1, but x is greater than or equal to 1. Okay, so x has maxed out on its probabilities, x is equal to 1, but y is still, you know, processing its values. fxy, fxy, this is 1 and y. Okay, so now I'm going to take my joint distribution where they're still happening, right? And I'm going to plug in 1 for x, and then what I'm going to get out is basically y, 1/2 y plus 1/2 y cubed. And then we'll put all the pieces together. I'll let you guys finish writing that, and then we'll tabulate it, okay, into looking like a piecewise function. Right, so we've got different combinations of things where x and y are greater than 1, x and y are less than 0. Okay, we've got the case, the meat of it, right, where x and y are both happening. Okay, they're both between 0 and 1. Okay, but I have to take a look. I don't know what their values are. Basically, y is between 0 and y, whatever the y value is. X is between 0 and x. I have to come up with that joint cumulative. This is the case where x is still accumulating, y is all done. Y is still accumulating, and x is all done. Okay, so I've got these multiple pieces that I've come up with for the different intervals. Okay, so let's go ahead and put all that together.
How would you set up like the integrals for those bottom ones?
Well, so we actually don't need to because I've already done it here, right? I can take this bit right here. So I've already got the joint distribution when they're both active. Okay, so I can use this one here. I don't really need to. I can exploit what I've already done. I can exploit what I've already done. So in this case here, right, x is still active, so this is still valid, right? But now y is just equal to 1. So I'm going to use this equation here, and I can plug in 1 for y. In this case here, I'm going to use this equation for when y is still accumulating, but x is all done, so x is equal to 1. So this is the harder one, right? Because both of them are active and both of them are changing, okay? But I can exploit this function here in helping me derive these bits. Okay.
And then how do you know when x is just changing and when y is just?
Yeah, so let's summarize it, and then we'll talk, because we have these different intervals where x and y are both happening. So let's put the pieces together, and I'll answer your question as we're putting those pieces together. So this is our joint cumulative distribution. Okay, so the first bit is it's going to be equal to 0 when x is less than 0 and y is less than 0, right? So these are our intervals. I'm going to put down on the right hand column, and then these are the functions that apply within those intervals. So that's our first interval. Then the next one is, we'll say 1/2 x squared y plus 1/2 x y cubed. And this is true when x is, still between 0 and 1, and y is still between 0 and 1. Okay, so this is the meat of it, right? Where they're both changing, right? They're both still accumulating values right here. Okay, so I've got they're both 0. I'm going to put down they're both 1. I've got they're both changing. Now x is changing, y is done, y is changing, x is done. Okay, so you're kind of thinking about the different combinations, okay, of what can happen with our x and y. Remember with our uniform distribution, we did that kind of like a little, like a graph, like the different quadranty type things. That kind of helps you. It was, let's see, right here, okay? So we were looking at, right, x and y are both less than 0. Okay, so our cumulative is equal to 0. X and y are both 1, so our cumulative is equal to 1. Here is where they're both changing, right, where it's a shaded area. Here is where x is changing, but y has accumulated everything, right? Y is above its spot, right? It's already accumulated everything. Here in this spot, right, x, basically x is done, but y is still accumulating. So we need to kind of think about what are our different combinations to take into account to get this complete cumulative joint distribution function. It's more complex because I've got two variables that are happening, and you can think about it like they're both 0, they're both 1, they're both changing. One's changing, the other's not. The other's changing, and the other's not. Okay, so I've got all these different combinations of intervals that I need to take into account. So that's the first one. Let's do the next one. 1/2 x squared plus 1/2 x. This is for when x is between 0 and 1 and y is greater than or equal to 1. Now the next one, 1/2 y plus 1/2 y cubed. This is when y is between 0 and 1 and x is greater than or equal to 1. You can see it, right? X is still changing, but y isn't, right? That's why we don't have any y's in there, because y is already done accumulating all of its probabilities. It's already maxed out at 1. Here, y is still changing, but x isn't. X has already accumulated all of its probabilities, so I just have y to think about. Okay, and then it's equal to 1 when x is greater than or equal to 1, y is greater than or equal to 1. Okay, so we've got our 1, 2, 3, 4, 5 different combinations, okay, for how I need to think about what's happening with my two random variables. Okay. I think I kind of answered your question, like how do we know these different intervals here? And it goes back to think about that box that we did for the uniform distribution. You know, what are the different combinations for what x and y can be doing?
Okay. One last question.
Mhm.
How is it x is just less than 0 and y is less than 0, but then we have x is greater than or equal to 1 and y is greater than or equal to 1 when the interval is
Yeah,
just...
why? I guess I'm being a little sloppy. I mean, I can even get rid of this. We're integrating, so it kind of doesn't, you know, matter. But I can say when it's equal, greater than or equal to. I'm sorry, this is greater than or equal to 1, and then I can do. I see what you mean. Yeah, we can do that. It's fine. We're integrating, so oftentimes these things, you know, aren't gonna we're not being held too hard and fast to it. But if we want to be you know, stringent about it, we can, you know, get rid of the inclusiveness on it.
Okay.
Okay. All right. So let's talk about independence. All right. So independent random variables. Okay. So what does that mean? So if we have jointly continuous random variables. Okay, that's like what we've been doing in this chapter, and that these are independent. Okay, what does that mean for things? So we would then say f of x given y is equal to simply f of x, right? Because if they're independent, right, then there's no conditional probability. It doesn't matter because x is going to happen regardless of what y is doing. I'll write that down. Since knowing the value of our y variable does not change the probability density function of x, because they're independent, right? X isn't dependent. It isn't conditional on y at all. Okay, so now because of this, so I can say I can write down f of x, y. Okay, this here, this is equal to f of x, right? So now what I can then write in conclusion is my joint distribution is equal to the product of the marginal distributions. This is the way that I can prove that two random variables are independent of one another. I can take their joint distribution, I can find their marginal distributions, multiply the marginal distributions together. If I get back the joint distribution, now I've just proven that these two random variables are independent. Okay. In a discrete case, so x and y are independent. We're going to write it as probability where x is equal to a and y is equal to b is the probability that x equals to a times the probability that y equals b. Okay. For every point AB. Okay. Just defining it's the same idea for discrete, okay, and for continuous. So we'll do this. Okay. If things are independent. Right, when you guys are ready, we'll take out our.
Let's say probability x equals a comma and y.
Yeah, I did the comma, which means and then I thought I'd write and too. Some kind of it's a little redundant. Yes, x equals a comma y equals b, or x equals a and y equals b. I'm working on my penmanship, but it's not quite there.
No, I just didn't see the end.
Yeah, I know. It kind of came out a little scribbly. When you're ready, if you want to get out your example sheet, we'll do example 9. We're going to try to figure out if x and y are independent given a joint probability density function. Okay, and we're going to exploit this property of things being independent. So we've got this joint function, 8xy, x, look at that. 0 is less than x, which is less than y, which is less than 1, 0 otherwise. So I'm going to just take a sidebar. We need to prove it with the math, but let's just kind of do things a little bit logically here. So I'm looking at 0 is less than x, which is less than y, which is less than 1. Okay, within this, that says x is less than y. X is less than y. That means that x is going to be dependent on y as a value. Our big random variable x is less than our big random variable y. So this means the value of x depends on the value of y. Okay, this is like a sidebar. We still have to prove it using math, but just logically, I don't know, kind of think about it ahead of time. So therefore, I'm going to think my supposition is that these are not independent, just based on how my range of values is defined. But I need to show this. I have to prove it, right? So we're going to show it. We're going to prove it with our marginal probability density functions. Okay, because remember, if they're independent, our joint density function should be equal to the product of the two marginal ones. Okay, it's not going to be based on how the range of values is defined, but we need to prove it. Okay, so that means xy, I'm going to put a question mark, f of x times f of y. Okay, I already think it's not going to be equal to, but I have to show it first. Okay, so first I have to come up with my marginal distributions. All right, so now to come up with my x, okay, I have to integrate my joint distribution, right, over possible values of x, but with respect to y. So now my x values, right, my x values are going to go from whatever x is, and it's going to max out at 1, okay, because it's less than y, which is less than 1. So x is going to go from x to 1, 8xy, and this is going to be with respect to y, right? Remember, we sum across all the y values. So that's going to give us, I'll show the antiderivative, 8xy squared over 2, and I'm going to go from x to 1, and that's 4x, 1 minus x squared. Okay, that's my marginal for my x variable, okay? So we can write that down as a function. I'll say f of x is going to equal to 4x 1 minus x squared. Less than 1, 0 otherwise. Okay, so there's my marginal for x. Let's do it again for y. Let's think about what y is going to be equal to. Fy. Oops, sorry, that's a y. So y, right, is going to go from 0 to y, whatever y is. So I start off at 0 and I'm going to end up at y. Okay, and I'm going to take my 8xy and I'm going to integrate with respect to x. Okay, because I have to sum across all the x values to get there. So now I'm going to get, let's see, 4x squared y from 0 to y is going to give me 4y cubed. Okay, so let's write that down as a summary. So fy, oops, sorry, this is lowercase f, fy, so y equals 4y cubed, and this is between 0 is less than y, which is less than 1, and 0 otherwise. I'll put a little box around that one, and we'll put a little box around this one. So you can see these are our marginal probability density functions for x and for y. All right, I can already see when I'm looking at it that it's not going to be equal to 8xy. So let's just write it down. So f of xy, question mark, f of x, sorry, you can't see that, f of x, f of y. So this should be 8xy. Is that equal to, I'm going to write it, 4x, 1 minus x squared times 4y cubed. And I can already see it's not going to simplify out nicely, right? If I were to multiply through, I'm going to get 16xy cubed minus 16x cubed y cubed, which is not equal to 8xy. Sorry, not equal to 8xy. So therefore, I can conclude not independent. We didn't think that they were based on how the range of values for x and y was defined, okay? But we needed to show it. You have to show it. It's not enough. You can't, if you have a question like this on an exam, you can't just write this and say, therefore, they're not independent. You actually have to go through the math and show it, okay? Using the property about the marginal PDFs, okay? And that's the end of chapter 3.7. We'll get as far as we can into 3.9 today, and then we'll finish it up tomorrow and start on 4.2. Okay. I'll post these notes for 3.7, the lecture notes. I'll scan them in, and then I'll post them up online. You know, after class today, probably sometime after office hours. That's probably when I'll have a chance to scan things in. Okay. Right.
What sections will the quiz be on?
So right now the quiz is set up to quiz us through 4.2. We can evaluate that tomorrow to see if we don't make it through the whole of chapter 4.2, then I'm okay with taking that off the quiz. It just gets bumped. Remember, each week we've got like a quiz or a test that's happening, so it just will get bumped into the next week. And I think next week is next week Memorial Day weekend. I think, yeah, next week is going to be Memorial Day, right? That so we won't have class on Monday next week. So we'll have to kind of take that into account. But let's try to go through. I think 4.2 isn't as long. Some of these, like the 3.7, has a lot of stuff in it, and I went through a lot of details to make sure that you guys got all the background information and things that you need, because there were nuances in there we wanted to make sure you had. And 3.9 has got some stuff in there too. So we'll see. We'll get as far as we can. But if it looks like we didn't finish 4.2, then we'll take it off the quiz. Okay. Great. Okay, so let's switch gears. So we're going to talk about chapter 3.9, which is further properties of the mean and variance. Okay, chapter 3.9. So we want to be able to think about topics that we're going to cover. We're going to talk about mean, variance. We want to talk about covariance, and we want to talk about independence again. Okay, some more details about these different properties, these different things. So we'll go through some notes and then we'll start working through examples for chapter 3.9. All right, so let's talk about independence a little bit. Okay, so we've talked about independence a lot. Independence is a really important property. When you go off into the world and you do experimentation, you want to make sure that your individual trials are going to be independent of one another. Having independent underlying data is really going to help you analyze your data and be able to make conclusions about it. So we actually work really hard in experimenting things to make sure that there's independence on the different trials that we're doing. All right, so let's say we've got random variables. We'll call them X and Y. We're going to say that they're independent if and only if, that's not a typo, if and only if the probability that X equals some value X and Y equals some value Y is the probability that X equals X times the probability that Y equals Y. Okay, this is our stated independence property, right? So otherwise, they are dependent. Okay, so it's an important property that we're going to keep working with. So let's talk about first discrete random variables. Okay, so we first talk about discrete random variables. Okay, so we're going to say X and Y are discrete random variables with a joint probability mass function EXY XY. Okay, and we're going to say if U XY is a function of these two random variables. I'm not going to define what U of XY is. I'm just going to say I've got some function, right, that has both of these variables in it. That's what U represents. Okay, so we're going to use this function U of X and Y to help us define further properties of mean and variance. Okay, but we should note that X and Y both have a joint probability mass function. Okay, so the first thing we want to talk about is our expected value of our function X, Y is equal to, remember, we're going to sum across all X values, sum across all of our Y values. Right, we're going to take our function of X, Y, and then we're going to multiply it by our joint distribution. This gives us our expected value of this function here. Okay. Okay. Remember, U is just some function that we've defined. It's the sum of the two faces on the die. It's whatever. I mean, it's some function that we're defining as we're taking into account these two random variables. Okay. So let's talk about how we're going to get our means out. Okay. So let's do this. If our function U of XY is equal to X, our first case, that means our expected value of X, right, I've substituted, our expected value of X is, I'm going to sum across all X, sum across all Y. This is my function, U, times our joint distribution. This is going to give me the mean of X okay, the mean of my random variable X. A lot of these are properties. Okay, we're going to talk about all these properties and then we're going to start using them in examples. Okay, so next one, if our function of our two variables is equal to Y, okay, that means my expected value now of Y is going to equal to, I'm going to sum across all X, sum across all Y. This is going to be Y times probability XY, right? And this is going to give us our mean of Y. Okay, of our random variable Y. Then we'll do it together. So I'll say if our function xy is equal to x times y, that means our expected value of x times y, right? Same thing that we've been doing here. I'm going to sum across all x, sum across all y, x times y, times the probability, the joint probability mass function. This is going to give us our joint mean. Okay, this is what we'll call the mean of our joint distribution. Okay. That's our expected value, which is another way of saying what's our mean. Okay. Give you a second to finish writing these down, and then we'll talk about our variance.
Can you go back just for 1 second?
You bet. Is that okay?
Yeah, I just need a
Let me know when you're ready.
Okay, thank you.
Okay, great. Okay, so let's talk about our second property, which is variance. Variance of x and y are two random variables. Okay, so first we'll deal with x. So we'll say if our function u xy equals x minus mu of x squared, right? This is, remember how we calculated our variance out. Then our sigma sub x squared, right? This is our term for our sigma squared is our variance symbol, equal to the variance of x, which is we're going to sum across x, sum across y. We're going to take this function, x minus mu sub x squared, times our joint probability function. Okay. Or we're going to use our shortcut, right? Our shortcut definition for variance. And we're going to say sigma squared, let's see, I'll write it down. Sigma squared x equals variance of x. Remember when we did these first out, we did them both methods. I thought this method here of expected value of x squared minus the mean, our expected value squared. Okay, this is a little easier, right? Because even though I have to calculate this term e of x squared, I have less calculations that I need to do, so I'm less likely to make a mistake. So this one here, but this is our shortcut, but I'll just write out what that means. This is sum across x, sum across y, x squared, ex, y, y. This is our e of x squared minus our e of x squared. Okay, so this is what we actually need to do to calculate this e of x squared. Okay, that gives us our, for our random variable x. Okay, we're going to do the same thing now for y. I'll start writing it, spelling it slowly. And now for y. So I'm going to say if our function u of xy equals y minus mu of y squared, right? This is our variance definition. That means our sigma y squared is equal to variance of y, which is we're going to sum across all the x, sum across all the y. I'm going to take this y minus mu y squared, and I'm going to multiply it by my probability, joint probability function. Okay. Or I can use the shortcut, okay, which is the same shortcut that we talked about for our x, sigma y squared. Our variance of y is going to equal to the expected value of y squared minus the expected value of y squared. Okay, which, plugging it all in, this is going to look like y squared x y by time, oops, minus mu y squared. Okay, so that's how we come up with it. And this is our y variance. Okay. You guys finish writing that. When you're done writing that, if you want to take out your lecture note examples for 3.9, then we'll work through example number 1.
Is that mu y and that whole value squared?
Where are you?
The second part of y.
Are you right?
Expected above that, expected value of y squared minus mu of
Like that. Yeah, this is like the shortcut that we did. This was like when we said expected value of y squared minus the expected value of y quantity squared, right? But we've just substituted, instead of expected value of y, we've called this mu sub y. Okay, so that's what we're talking about right there. Yeah. The shortcut I like, because it has less algebra and I'm less likely to make a mistake. But it's up to you. Both will work. Okay, you can make your choice. I tend to do this method, the shortcut method, in the examples. Okay, so I'm going to take a look at example 1. I'm going to scroll this up a little bit here. We're going to take a look at example 1. Okay, so example 1 says we've got 2 4-sided die now. Okay, 4-sided die. One is black and one is red. X is the random variable for the outcome on the red die. Y is the random variable for the outcome on the black die. What is the probability that X takes on a particular value, little x, and Y takes on a particular value, little y? So we're looking for this right here. Okay, so it's a little bit generic, but we're going to be able to come up with a specific number. Okay, so the first thing that we want to do when we work this is we want to think about coming up with our joint probability distribution. So I'm going to say find the joint probability distribution. Okay, so let's think about what our options are first. So X can take on the values. This is a 4-sided die, so X can take on the values 1, 2, 3, and 4. And then Y can take on the values 1, 2, 3, and 4. And we're assuming that these are fair die unless we're told otherwise. Okay, so then that means that X, Y, little case, is a particular outcome in our sample space, right? So let's think about what our sample space is. If I've got 2 4-sided die, it's not too much to enumerate these things, right? So I could get 1, 1, 1, 2, 1, 3, 1, whoops, sorry, that's a 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4, right? In the past, we did this as a table, right, with die 1, die 2, and we had these different table values here, and I just did it in a list instead of a table. Okay, so I've got, when I count it up, I've got n equals 16. I've got 16 possible outcomes. Makes sense, right? I've got four sides on one die, 4 sides on the other, right? Remember our combinatorics, 4 times 4 is 16. So 4 times 4 is 16 possible outcomes. Okay, and then I'm just gonna specify here that the dice are fair, because I wasn't told otherwise. So I'm just gonna make that assumption, which means if they're fair, then all outcomes are equally likely. Okay, if all outcomes are equally likely, that means that the probability that my X can take on a particular value and that my Y can take on a particular value is just 1/16. Okay. So let's do this. From here, we weren't necessarily asked to do this, but let's take on different possibilities for what we can do. So let's build the probability mass function for this, just so we can see what these things look like. So I'm going to say, let's build our probability mass function. Okay, and let's see what that looks like. So I've got the probability x, y, xy as my function. And I've got the possible values that my random variable x and y can take on. So I'll do x over here. So x can take on the values 1, 2, 3, and 4. And then my y values, my y random variable can take on the values of 1, 2, 3, and 4. I'm going to write y up here. Okay. Now what's going to happen is we're going to sum things up along the side, remember, and that's going to give us our marginal distributions as well. So I'll leave a little extra space for that. Okay. Doesn't look so great, but okay, so let's do this. So because everything is equal, right? We just said that everything was equal. I'm just going to fill in the table. So the probability that I could get 1, 1, which was this sample outcome here, is 1/16. Probability that I could get 1, 2. Probability that I could get 1, 3, 1, 4. Okay. Now, if let's just fill in the rest of the table. All of them have equal probability. So we'll fill in the rest of our table here. There. Okay. Now let's remember, we're going to come up with our marginal probability mass functions. Okay. So if when x is equal to 1 and I sum up across all the y values, right, I'm going to get 4 out of 16. That means that this column here is going to represent my marginal distribution for x. You can do the same thing for when x is equal to 2, when x is equal to 3, when x is equal to 4. Okay. Now I'm going to sum up here when y is equal to 1. I'm summing across all the x values. This is going to give us our probability mass function, our marginal probability mass function for y. Do that again for here, do that again for here, and do that again for here. Now look, if I sum all these up, I'm going to get it equal to 1. Okay, this is our sum. Okay. Okay. All right, so we've just come up with our, I'll put a little circle around here because that wasn't marginal mass function and our marginal mass function here. Okay, so we have our joint probability mass function and we have our marginals. The marginals we can yank up very nicely from our discrete table. Okay. So now we've got our individuals, right, our marginal functions. We've got our joint function. Let's take a look at expected values. These things weren't asked for in the original question, but we're going to answer them because it's good to practice this stuff. Okay, so now, what is the mean of x and the mean of y? Okay, so the mean of x and the mean of y, we're talking about expected value, right? Expected value is another way of saying our mean. Okay, so mu of x, okay, is our expected value of our x random variable. Okay, which means I'm going to sum across all of my x values, x, oops, sorry. Okay, I'm looking at my probabilities. Okay, for my probability joint, my marginal probability for x. I'm going to multiply it by the value x. I'm going to sum it up because this is discrete. I'm going to sum it up. Okay, so I'm doing this just for, I could do this with the joint as well. I'll write that down in pencil. You could also write this out, but we're going to save ourselves some time. And I would have to write, this is going to be x times our joint xy. And so then I would have to go through all of the 1/16th, 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 and sum them up for all of my x. This should be a y here. But this is going to look like 1 times 1/16th plus 1 times 1/16th plus, and so on and so forth for all the ones, plus 2 times 1/16th for all the values that my x can take on. Okay, and then I would have to keep doing that for, there's a lot in there, but I can summarize it just using my marginal PDF. Okay, so let's do this part here as the less things to add up. So I'm going to go, this is 1 times 4/16 plus when x is equal to 2, the probability is 4/16. When x is equal to 3, the probability is 4/16. And when x is equal to 4, the probability is 4/16, right? These are our probability mass functions for when x is equal to 1, when x is equal to 2, x is equal to 3, x is equal to 4. So I sum up and I get 40 to the 16th, which is 2.5. This is my expected value for x. Okay, it's not a probability, it's an expected value, my mean. Right. Do the same thing for y. We're going to say expected value for y, okay, which means I'm going to do the same property. So I'm going to sum up across the y's. I'm going to go y times the probability mass function for y. Okay, we're going to sum up all those different values. It's going to look like this one, just because of the nature of how this looks. 1 out of 416 plus 2, 416 plus 3, 416 plus 4, 416. Now, all these values I got from my joint distribution table and from my marginal probability functions. Okay, so this sums up to be the same, 40 out of 16, which is 2.5, which is mu sub y. And my expected value for y and my expected value for x. Okay. Then we'll talk about variance. Okay. What is the variance of x and the variance of y? So we've calculated the expected values for x and y, and now we want to calculate our variance for x and y. So let's remember, so our sigma x squared is equal to my expected value of x squared minus my expected value of x quantity squared. Okay, that's this value here that we just got. Okay, so now we need to sum this up. So this is going to be, I'm going to sum up across all of x squared, my probability mass function for x, minus my expected value for x quantity squared. Okay, so let's do this part here. So this is going to be 1 squared, 4/16, plus 2 squared, that's a 2, 4/16, plus 3 squared, 4/16, plus 4 squared times 4/16, minus 2.5 squared. I just plugged in the values that I had before. I'm going to sum everything up. I get 120 over 16. And that's my variance, not standard deviation, but variance for my random variable x. We'll do the same thing for y. Let's see, I'm sorry. This is, my bad. I forgot to subtract. Sorry. So 120 minus 2.5 squared is going to give me 1.25. And this is my, that seems kind of high. And that's my variance for x. Sorry about that. 120 over 16 is just the intermediate solution. Okay. So now when we go to do y, it's going to be the same thing. So we'll just do it out. So e of y squared minus uy quantity squared. Okay. So this is going to look like, I'm going to sum across all y squared probability of y. Okay, and I'm going to say this is going to equal to 1 squared, same thing, plus 2 squared, 4 over 16, plus 3 squared, 4 over 16, plus 4 squared, 4 over 16. So that's equal to 120 over 16 minus 2.5 quantity squared. This is my mu of y, okay? And then I'm going to get the same thing. 1.25 is equal to my, oops, sorry, mu of y, my variance for y, okay? That's a sigma. Okay. All right, and I think, let's see, I think I was gonna go into continuous random variables, but it's gonna take some time, and I think what I'd like to do is stop for now, and then tomorrow we'll pick up with continuous random variables. This was all just discrete, and then talk about the mean and the variance for continuous random variables. How do we calculate them? And then we'll talk about things like covariance, okay? And like I said, tomorrow, if we don't make it through 4.2, then I'm okay with taking that off of the quiz, okay? Well, let's see how things go tomorrow, okay? Any questions so far? Or if no questions, then I'll sign off, and then I'll see you guys in office hours if you have any questions about the homework.
Thank you.
How would you write the joint of the variance?
Yeah, so the
Like,
mean
would
of
it
the
just be like just regular like just a regular variance?
yeah, so if you want to do the joint variance, then what you're actually thinking about is we're going to go xy squared. So we're going to do the same thing. So we'll say the expected value of xy minus the expected value of xy. I'm sorry, this is expected value of xy squared, and there, right? So we would use, right, our formulas, we would think about it the same way that we have been for our individual variables, but now our joint distribution has x and y together, okay? So this would be xy quantity squared, and then this would be e of xy squared. And when we have to use the joint distribution, we wouldn't be able to use the marginal distributions for it.
Okay, will we normally be calculating the joint distribution for like variance and mean, or is it usually just an independent?
You know, I think we're going to go through some examples. We're going to talk about when things, when x and y aren't independent, right? You'll have what they call a covariance, right? Where x and y are varying, but because they're dependent on each other, they're varying together. We'll talk about that. This is later on in chapter 3.9. Mostly because a lot of the data that we work with, the underlying data are independent. Then we talk about the individual means, and we talk about the individual variances as we work it through. It's not often that I've seen that we work with the mean of the joint distribution, but like you would use the same calculations, but everything would be x times y to calculate. So the expected value of x times y, right? That's how you would then be calculating your joint mean, right? And you'd be using your joint distribution for that instead of your marginals.
Okay, thank you.
Yeah.
One more thing. If we don't get through 4.2 tomorrow, then are we not going to turn in for homework as well?
We'll take it off the homework, yeah, and it'll just be due a week after. So you guys will have like probably homework over the weekend instead of just being able to relax. But we'll see. Let's play it by ear tomorrow and see how things go. I suspect we'll be able to at least start it. But if we don't finish it, then I'll just take it off. Let's do this week. Okay.
Okay.
Sounds good.
All right.
Hey guys, I'll see you later.
Thank you.